Good morning, sir.
Very good morning.
I think it must be morning in the London.
Yeah, it's 9:30. It's 5 minutes to 9:30.
Okay, sir. Okay. So I am making you co-host, sir.
Okay. So I can share my slide.
Yeah. So we'll start at 2 p.m. as per Indian Standard Time.
Okay.
Just 4 minutes to go.
Let me get my.
So should we start, sir?
Yes, we can start.
Okay. Okay, sir. So let me introduce the audience with our today's presenter, Professor Bikash Pal. It gives me immense pleasure to introduce Professor Bikash Pal, a distinguished academic and researcher in the field of power systems. He is at present Professor of Power Systems at Imperial College London, where he has made outstanding contributions in power system stability, control, and estimation. He has led several major international research collaborations, including UK-China, EPSRC, NSFC program on sustainable energy systems, and UK-India consortium on smart grid stability and control. His research partnership include global organizations such as ABB, GE Grid Solutions, and UK National Grid. He has trained power engineers across the world. He has developed 68 bus power system model, which is now being used as IEEE benchmark for stability analysis. He has served as editor-in-chief of both IEEE transactions on sustainable energy, as well as IEEE transactions on power systems, as well as IET generation, transmission, and distribution. With over 135 IEEE transactions papers to his credit, Professor Pal's work continues to shape the future of sustainable and resilient power systems. With this introduction, I welcome Bikash Pal sir and request him to start his presentation. Thank you, sir.
Thank you, Professor Agarwal. Let me just share my slide. Okay. This Zoom, I need to go to the share. Allow multiple presenters to share. Okay. Yes. Are you able to see my slide?
Just me, no sir, right now not. मैं अपनी हटाता हूँ sir. Let me remove my slide and now it's visible, sir.
Okay, it's visible now, huh?
Yeah.
Okay. So this was our title, Robust Volt Bar Control in Power System. That was the title.
Sir.
This is the title, right?
Yes, sir. Yes, sir.
Okay.
Robust Volt Bar Control in Power Distribution.
Okay. So let me see. Okay. Are you able to see one slide or two slide or what? Just display settings.
It's two slides, sir. One is main slide and another is
okay. Now it's okay.
Now it's okay.
Okay.
Now it's okay.
So thank you for your time to attend my presentation here. This is robust volt bar control in power distribution. I'm sorry, this I did it. I got it's not that. I'll change that the first slide and send that to you. So this is the chance constant volt bar control. That is BBC problem statement, current challenges, and then I talk about the chance constant volt bar control framework, convexification of the power flow model, scenario enforcement algorithms, two-stage implementation strategy for this scenario enforcement algorithms, and then we'll talk about results and discussion. I think we have about more than an hour. How long is this time, Sanjeev ji? What is the duration of this?
1 hour, sir.
1 hour. Okay. So then I have to be a little bit quick. So BBC problem, what is volt bar control? The main objective is we need to keep the node voltage of the systems within plus minus 5%, and the feeders must not exceed their capacity, thermal capacity, that is maximum. Secondary objectives, we minimize the power loss, and then also we minimize the tap counts. So this is the second objectives. What are our control variable? Okay, let me get my pointer ready. Yeah. What are our control variable? Control variables are shunt capacitors, they're mechanical, and also the bank of capacitor. And then we also have onload tap changer and voltage regulator set points. We will have the distributed generator that will have the reactive power availability, so that can also be. That is the philosophy that voltage regulation is the responsibility of the distribution network owner and operator, and then we used to have some line drop compensation to make the voltage normal. Now we have these solar farm connected at this node through this inverter. They have variable amount of P, and then also they have the reactive power capability because they are all in the the voltage source control type of converter, where you can have switching on and switching off control. Since P will be changing because of the say solar conditions, if it solar irradiance, so Q also will change, but that change is very random. So Q also can be changed randomly to control the voltage. We have the transformer here, and between these two, how we can coordinate. Right. That's the strategy. Historically, the photovoltaic and load forecast errors were neglected. That variation in the photovoltaic and also the load forecast were neglected. So we could have a deterministic optimization problem formulated. But when I take these error into account, that becomes random or stochastic. Recently, the DZ allowed to actively participate in voltage regulation by IEEE P2800 standard. It is now P2800 standard. So we need to incorporate the DG reactive power support capability in the voltage regulation process. So how we do that? So this is our yesterday's deterministic volt-var control. We minimize the power loss. Power flow model, node P and Q deterministic. And this is 0.95 to 1.05. There was no forecast error considered. We have chance constant volt-var control. We could minimize the expectation of the power loss. Here now it's a stochastic environment, so we minimize the expectation of the power loss. The power flow model, node P and Q are not deterministic because we have the solar PV where P is varying, so will the Q will also vary. So that's uncertain. So that means if that happens, we cannot have just a simple inequality. We'll have that probability that node voltage is within 0.95 to 1.05 must be greater than this number, and 1 minus epsilon. And epsilon is something that we can design. So the forecast error are now have to be considered. In chance constant volt-var control, we minimize the expectation of the power loss subject to the power flow model is being, power flow constant is being met, and then this probability. If you look at that power flow model, this is non-convex, no guarantee of global optima. Why it is non-convex? Because we have all those power flow expression that involve product of the voltage, sine and cosine of the angle difference, and so on. So that's non-convex. This is a probability. How we compute this probability space? Probability that this is this. We cannot have this probability density function mathematically expressed, right? This one. So that's also the another challenge. So putting these two constraints to minimize this chance constant optimization flow just by mathematically solving this is not possible. So what we can do, we introduce the branch flow model, the Ohm's law, that is Vi minus Vj, Zij, Ij in a branch. That the power flow is Vi into Iij conjugate. Node power balance at any node is this. Whatever comes here, that is goes. That's the continuity equation. So now Sij minus Zij, Ij square That's the impedance of this branch. Zij into ij square is the loss. That minus this, that comes over here, right? Sjk, sum of this is what? This Vj minus this I conjugate like this. So this is your Sj, the node power balance. Eventually this, if I am injecting some amount of power into that, so that is this expression. So now let's see what happens. If I do this as, take the square on both sides. So this is Vj square is Vi square minus 2 Rij Pij plus Xij Qij plus Rij square plus Xij square into Iij square. So if I do take the square on both sides and then resolve this Zij into R and X, I get this. And on the branch flow also, if this is P plus Pij plus Jqij, so if I take the P plus Jij into P plus Jqj into P minus Jqj, so I get P square plus J square, and this is Vi I conjugate into Vi I. So that means this becomes Vi square II square, right? That one, this. So now, and here, that is S is P plus Qj, so you could factor into P into Q. So these are the complex expression in compact form, and here are the real and imaginary part. So this is how it is now we could organized. So you see one thing here. Let's see. Yes. This Vj square, Vi square, Pij square, Qij square, Vj square, Vi square, Iij square. This square here, if I redefine as a new variable, Lij, and this Vi square is Ui. If I do this, then what happens? So they come over here. You see that Uj minus Ui, 2Rij, like this. Pj is Pjk, etc., etc. And now Pij square is plus Qij square is Lij Uj. So this expression is kind of this. Now we have a convex expression. This is convex in U, L. This equation is absolutely convex. Look that this is all linear, right? These are all parameters. This Q, P, U, L, it's a linear, absolutely. Here it is linear. X, this is a parameter, Q. So all are linear, except this one where we have a nonlinearity. How? You see that P square plus Q square is equal to product of Lij Ui. So that means this is still nonlinear. What we can then do, this is again the expression of a circle, okay, in PQ plane, where the radius is Lij Ui square root. So that we can do as less than. If we do that, so that becomes actually a convex cone if it is a less than. And once this is that, one can always break this into 2pi, 2qi, Li minus ui, Euclidean norm. If we take the Euclidean norm, what we get? This is 4pi square plus 4qij square minus Lij plus Lij square plus ui square plus minus 2 into Lij ui. If I take the square of that and take the square of that, that becomes Lij square plus ui square plus 2 Lij u and u square. So this then we could cast this as a second order cone. Just take the Euclidean norm of this, take the square and then adjust, and you come to that, because here would be minus 2 Lij ui, here also will be plus 2 Lij ui. That minus 2, if you bring it to this side, that becomes 4 Lij ui, and this is 4 Pij square, 4 Qi square. Then you can eliminate 4 from both sides and you are back to that expression. But this expression is the expression of a second order cone. So from nonlinearity, we have been able to relax the equality into this inequality, and we have got a second order cone. So once we have that second order cone, then we can have a convex programming. Constants are in Pi, Qi, Li, and Ui. So this is what we need to work. There is one problem that we have the capacitor bank. They are not continuous. The shunt capacitor bank, the model of that would be susceptance, right? So that susceptance B into V square is the Q that comes from the shunt capacitor. That susceptance is not a continuous value because there is a bank of capacitor. So that BCJUIJ, particularly where here this QJK, this will have BCJ this. That means this is kind of not a kind of continuous variable in the linear space. It is the mixed integer. So not all BCJ uniformly will be acceptable. So this is that we need to do a big M method for bilinear terms to linearize the product of a continuous and a discrete variable. So we replace that for a particular, this J is the jth node. BCJ is the capacitor bank. That capacitor bank may have 3, 4, 5. So those discrete value. We come with this BCJ as ZJ1, ZJ2 like this. What do I mean by that? At any point of time, you will have one particular bank, one particular capacitor that will be engaged, not all of them, right? You switch into one, like there are 4 or 5, so you just switch into say one set. So that is it, that is how we are giving this as an index of binary index of either 1 or 0. So this that ZJK BCJK UJ, so that means at any point of time you will only have one. So for that ZJ would be 1, and the other one which has not been included into that jth node on the bank, they would be 0. So this is how we now are trying to treat this. So we define a new quantity called Wj, which is ZJKUJ, that is BCJWJ. So Wj is a new quantity which is that binary into that voltage, and that would be right BCJWJ. Okay, ZJ, and this one is WJ. So that K is equal to 1. So now we have this, like when ZJ is 1, that is that particular bank has been selected. So when that is 1, so 1 take away 1 is 0. So UJ is less than WJ is less than UJ. So that means, so ZJ1 means this is also Uj. So Uj less than equal to Uj less than equal to Uj. So this inequality collapse. And here minus M less than say Uj less than plus M. So Uj is the voltage square. So that would be around 1. So now this in this expression minus M, a very large number M to a very large positive value. So that 1 is between this minus to this. So this is satisfied and that disappears. So when it is Zj is equal to 1, when Zj is equal to 0, so then that means here 0 means this expression, collapses, and this one Uj minus M is less than Wj less than Uj plus M. So this is 0. So Uj minus M, M is a large quantity but negative. So with a 1 minus that large negative is still a large negative, and with 1 minus with 1 plus that large negative is still a large positive high value. So a large negative to a large positive, Wj is content, where this is what our Zj was 0 at that, so Wj is 0. So 0 is in the sitting between the large negative to large positive. So this is how two condition. When the capacitor bank is engaged, that is 1. So the second expression hold, and when the capacitor bank is not engaged, that is 0, then the first expression hold. So the security constant probably the probability space. What is this? Difficult part is the probability that this node voltage should be greater than 0. Difficult to compute. What is the probability density function for this node voltage? We do not know. The easy part would be that probability density function of PV forecast errors. That if we know the forecast error from the historical data to a good accuracy, then what we could do, we could generate many scenarios for power flow, and then we could include those scenarios as a constant in that optimization, and then see that if all the constraints are satisfied, for what sort of transformer tap position, what sort of capacitor bank voltage positions, and also what reactive power output position from the PV. So then we could do a large number of scenario, then it should be fine. Proposed optimizer, the probability spaces, scenario-based approach. No reformulation is needed. Lots of scenarios to be considered. So how many scenarios are lots? So that means if we have B number of binary variable, that is capacitor bank position, and C number of continuous variable, that is what I would say that the reactive power set point, and also continuous the voltage regulator point, not the tap position. Taps are binary, capacitor banks are binary, the other variables. So then we need to have n number of scenarios where these expression hold, the epsilon and gamma, actually this. So OLTC, capacitor, and QDG satisfy all scenarios if we have n number of these with a confidence that is 1 minus gamma, and epsilon is the level of robustness. So these two quantity, the confidence and robustness level, epsilon and gamma, we can define. So what is the confidence that if I that means if I have n number of scenarios, within that n number of scenarios, I can say that with this much of confidence that the results that I am getting, that we will not violate actually the voltage limit, and with epsilon level of robustness, this means, I mean, you would get a solution with 1 minus epsilon. That means percentage, I mean, that much of percentage time multiplied by 100, that those many cases you would always get the solution that would satisfy this thing. So this is the confidence parameter gamma and robustness parameter this. Or in other words, we would say that n number of scenario that if we choose, we can say that with 1 minus 10 to the power of 6, whatever it is, that with that percentage, that all the violated scenario would be included. And then the robustness is that the solution that we get, that will actually meet the desirable the feasibility. Okay, I say it again. you can have infinite number of scenarios with this, but n is not infinite. N is very large, but not infinite. So whether within that n, all the scenarios would be included or not, that comes from this gamma. And the solution that we get, whether that solution is the feasible and give me the solution within with a voltage profile between 0.95 to 1.05. So that is called robustness. So these are the two parameters. So now let's cast the optimization problem, the discrete controller. So we now have minimize the expectation of the loss. Plus, we must make sure that we don't let the mechanical device like OLTC or capacitor bank, particularly say OLTC, does not change very often with the change of the solar injection. The solar injection is changing a lot. The reactive power, real power will change a lot. So transformer tap would adjust to maintain the voltage. So there also we need to put some constraint. So that would be tap new minus tap old. Okay, so how we do that? So this is the tap new position and old position. Now these are all position. Okay, these are all the binary position. So how we do that? So we have here an expectation function, and here we have this integer, the modulus, yeah, it is essentially a number. So this we can handle with epigraph programming, where we can do minimize W1 into expectation of power loss, W2 into T. We define a new variable called T. Minus T is less than tap new minus tap old less than cap T, and this T has to be positive, greater than 0. So this is how we are relaxing this from modulus absolute value to tap new minus tap old. So minus this to this. Okay. So that is our new variable is capital T, and which is a positive quantity. There are other hurdles that you have to pass. That there are three types of load: constant impedance, constant power type of load. This is P alpha ZP alpha ZJ For Q, beta JP beta JZ into U. So this constant power is not function of voltage. Constant impedance is function of the square of the voltage. So we have defined the square of the voltage to our new variable U. So these two loads type are absolutely fine in the convex program. But if you have a constant current load, which is just a linear function of voltage, and that voltage square has been defined as a new variable U, so that means that load is becoming now square root of U with the new variable. But then again, that means that is bringing the nonlinearity, non-convexity back. So how we deal with the constant current load? That's one aspect. The forecast error of the load we can assume to be Gaussian in nature, and then we will see what happens. So auxiliary variable are U and L. Voltage dependent load G alpha P alpha Z V square alpha I V. So this and this is fine. And exponential model P0 V to the power of beta, as long as beta is either 0 or 2, we are fine with that convex. But if beta is 1, then we need to see how we could handle that. So that is the voltage dependent load. If we neglect that, the voltage dependence is neglected, constant power load assumed. So then what happens? So this is your ZIP. This is magnitude of the voltage versus power. Now that black is constant power. Irrespective of the voltage, you have constant power. This one is ZIP, that the blue, and this is the exponential model. So everyone is matching at 1 per unit of voltage. Normally we will be operating around that region, right? The voltage, this is 0.92, but sometimes it, sorry, this is the power. So this is 0.9. So when the network is operating under stressed condition, that is very low voltage, say 0.93 or something, we can come over here. When it is operating at more than 1.05 up to 1.1, then we can go over there. But normally we'll be here around that. Let's see how we can handle this. Oh, but it is not. Okay. Yeah. Voltage dependence in convex solver, how the V square is available. So this ZP is alpha P, alpha Z V square. Now, what we can do, we can express through binomial series any quantity x, 1 plus x to the power of delta, can be written like this. Assume that your voltage is 1 and your around 1 and x is your delta V, that is your deviation of the voltage. So that 1 plus delta V, delta, if you do power network under normal operating condition, the V to the power of n, that is V is V0 plus delta V to the power n is 1 plus delta V eta. This is equal to 1 plus eta into delta V, right? If you take the first approximation, first term. So the good approximation will be that delta V is very, very less than 1. N of delta V will also be very, very less than 1 when you are very close to this. So that is the binomial approximation for that. So once we do this here, then we could absorb that alpha current I part, alpha I by 2, alpha I by 2 into constant power part and constant voltage part, half and half. With that approximation, you can take that. So constant current load part get absorbed 50-50 into the power part and also the impedance part. For an exponential model also, it can be done. So just applying that approximation. So now this becomes your new alpha 1p, that half of that has been absorbed. The alpha zp, this is this. So then we do this and then that. But when we are very far from 1 power unit, that is delta V is not negligible. So then we are very far, that is under stressed condition, we are operating at 0.94 or 1.1 something. Then the binomial approximation method, BAM, will be in less accuracy. So we need to go for the linear least recursive model. So that is, then we estimate the model, etc. We find actually these various quantity, like we need to have an estimated model of alpha P, alpha Z. This is impedance part, this. So we can have, like, for different value of V1 up to Vn, say V1 we can go from 0.9 up to say 1.1 with 0.001 sort of say resolutions. We can put that value here and then we see. So we put some value here, get this matrix capital V. Alpha P prime, alpha Z prime is what we need to estimate. Actual model, if we know our actual model of Jeep or exponential or Jeep model, we put that V, say 0.91 up to 1.1 or 1.0, all the values, and we find out what is our P, both for the Jeep model as well as from exponential model. So that is P1, P2, Pn, and then P. Okay, so that is the P we got, right? And this estimated model is giving us this, that is, you can say that AX is equal to that P. So how we solve that, right? So this V into this is equal to that P. Now we will have some error that we could put that residual. Now that residual error we have to minimize. So the LRM minimizes that residual. That gives you this V transpose V minus V transpose P. This is nothing but the normal equation you do in weighted least square. That's the normal equation. If you have AX is equal to B plus residual, how you can find the solution? Your solution is that A transpose A inverse into A transpose into that B. That gives you this estimated quantity. So this for a Jeep load, then you could put all these values V1, etc., and alpha P, alpha Z, alpha I, etc. you can find. And then this is giving you that, you know, alpha P, alpha Z, alpha I, you now know your V, and you put this matrix W, so you get alpha P hat and alpha Z hat. So this we can do, and there are some more way of getting this expression into proper sort of format, like how you get this C is this expression, minimizing this expression, finally you get CZV. Like there are some kind of the algebraic manipulations here, and then you can get that, and V is this, and then what we call as a V2 is Kronecker product of these. So essentially solving this, okay, that that capital C, that capital C for Jeep load is that CPV, and then this, okay, and then this is your CPV for constant power part, and the CZV is for the constant impedance part with this expression. So you finally get actually alpha P hat and alpha Z hat for Jeep, and then also you can get it for the exponential module. So now if you come to this, here you see that ZIP is the red, constant power P is this. Now we have the binomial approximation method, that black, the black one, and then this your red one, that Jeep. Okay, if you see that Jeep and this black one, around this 1 point per unit voltage, that is very overlapping. Red and black lines are very much overlapping. That means approximation is very good. More and more you move this way, you see that red is deviating from the black. That means BAM is not giving you that proper sort of accuracy. So then LRM, if you see that LRM is the green, and you see that LRM is very close here to the red, whereas black is far from the red. So LRM is giving you good accuracy even at 0.85. You see that? So that's how it is. This was Jeep load. And for exponential load, again, the exponential load is the red one. So that's our, say, benchmark of the load. Then the BAM is giving very good accuracy in this range, normal operating range. But LRM is giving good accuracy in the outside the normal operating range. So now we came to a conclusion that the constant current part of the load can be absorbed with the constant power and also the constant impedance part by getting actually those values, and getting those values by two methods. One by BAM, when we are not very much far from the normal operating range, and by LRM, when we are very much far from the normal operating range. So now let's look at the scenario enforcement algorithm. So we have many operating scenario that we have to do. So let's see how we can pick out this. Let's start initialize the solution scenario set by base case scenario. That means we take a particular operating conditions. There are many chat. I will attendance link. Okay, fine. There's no question. Initialize solution scenario set by base case scenario. We can perform the volt-var control. Our decision variable or discrete TIJ, transformer tab. VCIJ is our the capacitor bank position. AJ, BJ, CJ, this is, I'm coming to that, this is the expression between a relationship between the reactive power and real power of the DG. So with these, we can form the admittance bus matrix. We do current injection based power flow solution. So we can then factorize this Y bus as LU, okay, the lower and upper triangular factorizations. We now have the forecast error. It can be 5% error, 10% error, 15% error. On that error, with that error, we generate millions of, say, demand scenarios. Forecast error, both for solar solar generation, as well as for load. So with that generation and then scenario, we can have many scenarios. We can have, say, 100,000 of scenarios. So then we take each of those scenarios to see whether the security constraint has been violated. What we have, our base case is y bar, I is equal to yv. That is our solution, right? Current injection, I is equal to yv. So we know y, its LU factor. Now I is what? The current injection. So we have taken a value of the load, and that load for 1 per unit of voltage or whatever, we get the current I. So we know that I, we know the Y, so let's find the V. So are we getting this? So how you get, the VI conjugate is equal to P plus JQ. So then what you do, you have taken a P and Q on that forecast error, divide that by V and assume that V is 1 per unit. So you get an I. Put that I as a B and solve AX is equal to B, and X is your voltage. See whether that voltage is within the limit, that is 0.95 to 1.05. Do that check for all hundreds, thousands of scenarios. That's a check. Now, once you're doing the check, some of the cases will violate, some of the cases will not violate. Most of the cases will not violate. Say out of 100,000, or you see that, say about 1,000 cases have got violated and others have not. So number of violated scenarios, if none of them are violating, that means this solution of transformer tap position, capacitor bank position, and then reactive power set point in respect with the real power of the DG is able to cater all the forecast error and all the scenarios. If that does not happen, which will be the case, that it will not be able to, say, meet the constraint, it will violate the scenario. So then you have the number of scenarios. So say the number of scenarios that have been violated is 10,000, say. So now, will you do that 10,000 scenario as part of the chance constraint, again, putting each of the scenario as a constraint of that mixed integer, that multi-objective optimization? If this number is 10,000, naturally, it will slow up the program to have all 10,000 in the constraint. So what then you need to do, out of those 10,000 scenarios, can you choose some dominant scenarios? Like if there are few scenarios which are very close to each other, then take one of them. So how you do that? That again you do from the distance, like take one scenario and see the equilibrium distance of the other scenario from that scenario. Set a threshold that, okay, if this distance is less than this, I'm going to club all the scenarios within this distance space as one scenario. So that is how you need to reduce this scenario. And then add those reduced scenario to the solution scenario set. Here, run the scenario based chance constant optimization. What is the scenario based? That means in the constant equation of that convex power flow, you add those, each of the scenarios, P plus JQ. So that then gives you again a set of A, B, C and Tij, BCj. And with that scenario, when it is done, you get an ABC, Tj, then you go back. Why do you go back? Because remember, you have reduced the scenario. So you go back, and with that impact, the transformer tap position and capacitor bank position impact your admittance matrix. So we have a new admittance matrix. Again, we have to LU factor that admittance matrix. and then come back here and again check with those all the scenarios. Because this time some of the scenario which has not been violated in the previous check may be violated, because you now have a different this TJ, BJ, CJ. So again check all 100,000 and you see how many have been violated. You will see that if last time 10,000 were violated, this time maybe 1,000, even less, will be violated. Keep on doing that, and then finally again ABC and do this, and then finally after 2-3 iterations you will see that maybe 4 or 5 scenario will be violated. Then put all those 4-5 scenario without further reduction and then get a new ABC and TJ. That's how you solve. So perform VBC, check violated scenario, then reduce the scenario, add most dominant scenario to the program, run scenario based chance constant, improve the schedule, check the violated scenario. So this would be looping here, 3 or 4 loop, then you get the solution. Okay, let me see. Oh, fine. So now the philosophy 2 stage. So in the beginning of an hour, capacitor and OLTC tap position is fixed, then it goes down, goes up. So what does not change? In the beginning of the hour, your tap position and also your capacitor bank position remains fixed. Don't do anything for the whole hour. Around that hour, what is happening? The QDG, that is the reactive power of the DG, which is now function of PD, that's the expression. QDG is A PDG square V plus V PDG and then C. Okay, so that is the expression, and so that adjust. Okay, so this is the first stage control, second stage fine control. So with this, let's see how this process approach gives you better result. Voltage violation probability is the fraction of the total node voltage violation across all the Monte Carlo trial. So for deterministic case, and this is chance constant case, say we have n number of Monte Carlo trial, right? Okay, n number of Monte Carlo trial. So let's take a node which has got n number of node, n bus system. So if in every trial all the voltages violates for n node system, so for n Monte Carlo trial, n MC into NB would be the total number of maximum violations. Like if I have 1,000 node system, so maximum number of node that would violate is 1,000. Now for n number of Monte Carlo trial, for if each of them violates, then that would be the maximum total violations. So now we see for each of the trial, if the violation is NVVI and add them up, so then you get VVP. That is your voltage violation probability. Number of Monte Carlo trial, number of voltage violation in MC trial, and number of buses. Now you see that we have a 95 node system, UKGDS. In that, when you go that this deterministic case, this is violation is about 6%. So I would say that about 5 cases we have violated. The probability, this is the voltage violation probability in the y-axis. 5%, 6% cases we have violated. Whereas if we go with the chance constant, you see that that is the height of that, the green box bar. You see that we have not violated. This is this. Okay. Similarly, for IEEE 123, this is the violation, this is this. For 190 bars, this is the thing, and this is this 0.1. So now this is the past yellow, green, yellow, green, yellow, green. So what are the other yellows and other green? They are for different standard deviation of the forecast error. This is 0.1, this is 0.15, this is 0.25, and this is 0.15, 0.2, and 0.25. So that means if I relax the forecast error, like again, if I go back to that, see the forecast error, percentage of the forecast error. If I increase the forecast error, so naturally my scenario, etc., would be different, and then I can get this. So this is your standard deviation of the forecast error. We said that the forecast error is modeled as normal Gaussian distribution, unimodular Gaussian distribution. Okay, so that is so that. Okay, so now what happens? We had two things that we must not, do the too much of tap changer movement. So this is the weight between the tap changer and the loss minimization. That is the priority. W1, W2. You remember that multi-objective optimization. W1, if it is a 1, that is loss minimization is our highest priority. At that time, W2 would be 0. That means we don't care about transformer tap movement numbers. So that is that. If W1 is 0.5 and W2 is also 0.5, that means we are giving equal priority to loss minimization as well as restricting the number of tap movement. So this is when this is W1 is 1, that is W2 is 0, then you see that transformer tap changing is almost 24 cases. When we put 0.25, that is we give a quarter, 25% priority to this and 75% priority on loss minimization. This has come down. And when you go to like 75%, that is tap movement restriction is the first priority. We see that this number is less. So this is how the switching count and etc. that happens. So you got to have the in between, that is what should be these things. There is also the loss. The conservative index gives the fractional increase in the network losses for the chance constant, because conservative this one that gives you TJ, A, B, C, etc. from this chance constant, it is suboptimal. Best case, for one case we had the optimal T, B and ABC. So naturally, this being a suboptimal, so the loss also would be slightly higher than that deterministic case. So this is the conservative index. PLCC, that is chance constant, the total power loss, and the power loss on the deterministic case. Deterministic case power loss will always be less than this PLCC. Divided by PLDC, that is a deterministic case. So expected value of power loss corresponding to the chance constant schedule, expected value of power loss corresponding to the deterministic schedule. So as we move along with the different forecast error, you see that for three sort of system model, we move like that. So more and more we allow the forecast error, the losses will be impacted. So the results, nodal uncertainty need to be considered in the VVC scheme, more important than ever. Chance constant VVC framework can be effectively solved through scenario enforcement algorithms. This shows robust performance. Two-stage control structure introduced to give additional resource opportunity, and voltage dependent loads was needed for improved convex solver, because that we show you that constant current load, how that can be factored or absorbed into constant power and constant impedance, because we are in the convex programming where we have a new variable, voltage square and branch current square as our new variable to do the convex solution. This is my group, and we have this, and this is the man who did all the work, Dr. Firdaus, and he's still partly employed at Imperial, but he's associate professor in Glasgow, Caledonian. Other people are on other, I do on area, work in other area, but let's not talk about that. Let me finish this and give you some time to ask me question. So do you have any question? Stop sharing, because I know I'm exactly on the top of the hour.
So is there any question? I request the participants to ask questions if there are any. I have just one small query. This is predominantly distribution systems which are having solar systems, distributed generation within the distributed generation within the distribution system.
Yeah.
Yeah. So can we also have this sort of optimization problem with EVs within the distribution systems?
Yes, you can, because whenever you have EV is a load. So this one consider the forecast error of the solar generation as well as the load. Okay, as well as the load. So both of them are considered that with that sigma of 10% to 25%. So when you connect it to the distribution system where you don't have solar, but you still have the EV, which is a variable demand.
Yes, sir.
So this is absolutely possible. And also that EV comes with a variable P and Q. I mean, EV can also provide you the reactive power.
Yes, sir. Because it can be, if there is a bidirectional charger available, then they can act as V2G source as well.
Yeah, V2G, then they have a P here, there, but the EV, if it is just an EV that charging this, so you will have the variation of that P. That means your demand. So we have taken demand forecast as well as the solar forecast error into consideration. So if you don't have the solar, so you still have the demand forecast error. So that means this is absolutely applicable.
Any other question from any participant? Sir, I request you, sir, to please share this presentation with us so that we can upload it on AICT website.
Okay, I'll do this because I have that ID Guwahati thing. I just do that and then I'll send it to Deva Prasad. I have his email. Thank you. And also, I want to take this opportunity in this 55 audience, if there are some PS member, which I'm sure. Thank you for supporting the elections that I have won. And with all of you, I'll like to work together and make PS more relevant for India.
Thank you, sir. Thank you. Thank you.
Thank you, sir.
Okay. I'll email it to Deva Prasad. Okay.
Okay, sir.